How's everyone doing?
Great.
Glad to hear. Any questions, concerns, needs, etc., anything at all before we get started, including but not limited to homework questions? All right. Well, do please interrupt me when, again, if any and all questions occur to you. Main focus for this week, we are in chapter 7. This is one of 2 chapters about rotational motion. So this week we'll focus primarily on rotational basics, and then next week we'll get a little more into some of the weirder aspects of rotation, some more niche applications. So chapter 7, intro to rotation. Chapter 8, applied rotation. And then we'll be moving into Thanksgiving test 2 territory. On Friday, we began looking at these rotational basics, primarily defining the most introductory variables and definitions required for rotational motion, and looking at the direct parallels between rotational motion and linear motion. Namely, all the motion we've talked about so far is linear in nature. We're displacing in straight lines, having a velocity in straight lines, and accelerating in straight lines, and then some more specific applications of those concepts. Rotationally speaking, all those same basic concepts exist. We just replace the notion of moving meters forward with spinning radians rotationally. So, delta theta is angular displacement. Again, angular is a synonym for rotational, and I'm going to use the 2 words interchangeably. I apologize. Delta theta represents angular displacement, meaning how much has something spun, the number of radians or optionally degrees something has rotated through. Omega represents angular velocity, namely how much has something spun in an amount of time. Similarly, things like rotations per minute tells you how much something has spun per unit time. So the RPM meter on a car is a measurement of angular velocity. Then angular acceleration, I'll point out again, this is supposed to be alpha, not lowercase a. It looks slightly different. Alpha equals change in angular velocity over time, because if you are changing speed at all, either linearly or angularly, you are still accelerating. So if something starts spinning faster or starts spinning slower, then it is undergoing an angular acceleration. And all 3 of these concepts relate to each other in the same way that the linear versions do. So those first 4 formulas we covered all have rotational counterparts where we replace the English letters with Greek. Does this all feel familiar from Friday? No way? All right. Now this week we're going to set about applying this information, and the first concept we are going to cover is one that you'll be using in lab this week. So the bulk of today is going to be spent discussing the concept of centripetal force. So, before we get into that, I want to stop again. Does anyone have any questions or need anything before we get started with the bulk of today? All right. So, I want you guys to take a look at these pictures and tell me what they all have in common. We've got someone swinging a can by a rope over their heads. We have the moon orbiting the Earth, and we have a bunch of cars all driving in a circle. What do all these things have in common?
Rotating in a circle.
Something is rotating in a circle, very true. Namely, one thing, or I guess in this case, several things, are all rotating around some central point outside of themselves. Because as it turns out, there's actually two different types of rotational motion. You've got this type, where one object rotates about its own axis, and it's not actually really moving anywhere linearly, it's just spinning in place, rotating about itself. But then you can also get situations where objects that are not circular, objects that are not wheels, are capable of moving in a circle around something else. And so, to begin our discussion of rotational motion, we're actually going to look at a situation that is kind of both rotational motion and linear motion at the same time. Because in each of these three cases, the object that we're to discuss in each picture, the can here, the moon here, and the cars here, they are rotating about something, but they are also moving normally through 3D space at the same time, right? As the can circles around overhead, it does move from point to point within a two-dimensional plane, so it has XY coordinates that are changing. Same with the moon, same with these cars. So this is kind of a weird hybrid of angular rotational motion and linear motion, because both are kind of happening at the same time. This happens because of centripetal force. This happens because in each of these scenarios, there is a force making the object do this. These objects themselves aren't wheels. They don't have an innate tendency to spin, right? And yet, in all these scenarios, the objects in question are moving in a circular pattern around something. Literally, a force is making them do that. What force is going to make this can move in a circle in this picture? Person's hand. How is the can connected to their hand? String. And what do we call the force that a string tends to exert? Tension. Very good. So in that picture, tension is constantly going to be pulling the can towards this person's hand. And as a result, that can is always being pulled towards that person's hand as the can is spinning around. The can might never reach their hand, but there's always a force drawing the can towards their hand. In this picture, what force is causing the moon to orbit the Earth? Gravity, very good. And so even though the moon is constantly trying to move away from Earth, Earth's gravity is constantly trying to pull the moon back to it. So gravity is kind of acting like an intangible leash. Here, this rope physically is kind of acting like a leash. Here, gravity is metaphorically acting as a leash. And then in this picture, I'm going to go ahead and tell you what force is happening here because it's a little harder to see with cars on a road. Whenever you are in a car and you physically turn the steering wheel, you are changing the direction that the car's force is applied to the ground, and you are also therefore changing the direction that friction acts on the car because you've changed the orientation of the tires. So in this scenario, by changing the direction of the steering wheel, you are actively changing the directions of both the applied force in the engine and friction, causing a net force inwards. So in each of these cases, there is some inward pointing force causing all these objects to move circularly. And without that force in each of these pictures, would these objects be moving in a circle? No. If I come and physically clip this string, what direction is the can going to move in? Out and forwards. All objects want to move in straight lines, and so if it wasn't for that rope, the can would just do that. This is how ye olde David and Goliath slingshots would work. You would put a rock in a sling, swing it over your head. The sling physically keeps the rock moving in a circle until you let go, at which point that tension is no longer applied. the rock's own inertia and momentum take over, and it just takes off in a straight line. Objects want to move in straight lines. The moon wants to move in a straight line, and all these cars certainly want to move in a straight line, but something is literally forcing them not to. It's a different force in all these scenarios, but regardless of the forces having different origins, they are all doing a similar thing. They are all forcing these objects that want to move in a straight line, and they're taking all those objects and forcing them to move in a circle, orbiting some other central point. All this preamble has been to define centripetal force and centripetal acceleration. One sec. Modifying my notes slightly. This tends to happen when I have two different versions of the file and I load up the wrong one. All right, so these circular accelerations, because all those objects are accelerating in a circular shape, are caused by a phenomenon known as centripetal force. I assume you might have heard this word before. There's another word we're going to compare it to in a minute. But go ahead and get centripetal force written down, spelled like this. Centripetal, P-E-T-A-L. All the images from the previous slide have some real existing force serving the role of a centripetal force. All those pictures had a different thing: tension, gravity, and net force from the tires on the vehicle in the case of the car. It's all a different thing in each one, but they all serve the role of a centripetal force. And the main thing that a centripetal force does is it causes, something called centripetal acceleration. Because all of those objects, the can, the moon, and the vehicles, were accelerating. By definition, they were accelerating. To kind of illustrate this, I'm drawing the moon and the earth so that I can stay on this slide. We know, you should have been told several points by now, that the moon orbits the earth, and this happens because the earth is exerting a gravitational pull on the moon. So, at any given moment, Earth's gravity is trying to pull the moon towards the center of the earth. Why does this not pull the moon out of the sky?
Because there's gravity in the other direction, or like a force in the other direction.
Because it's orbiting around the Earth.
Okay, to acknowledge both of those comments, there are other forces on the moon, but they're caused by objects that are very far away. The Earth's gravity is the strongest force acting on the moon. So you're not wrong. And the moon is also exerting a force on the Earth, but technically the moon is also pulling the Earth towards it. So the net force overall should cause both objects to drift towards each other. And we don't see that happening. We don't see that happening because the moon is orbiting the Earth. And the reason that the moon orbits the Earth is because while this is also happening, the moon also has a velocity pointing in a direction. The moon wants to be moving in a straight line. And we know that all objects want to move in straight lines because we've talked about inertia and momentum. If an object is moving, it wants to keep moving, and because of momentum, it wants to keep moving in the same direction, correct? So the moon, eons ago, was given momentum, it began moving, and it wants to stay moving. It's been moving ever since it formed. So it has this innate velocity imparted to it by its own momentum, while Earth's gravity is pulling it towards us. Both of these are happening at the same time. And the fact that they're happening at the same time is what causes the interesting centripetal acceleration that we're studying today. Based on the way that I've currently drawn this picture, the moon's velocity points to the right, but the net force acting on it pulls down. So its initial velocity points to the right, there's a force pulling it down towards the Earth, and that means it's going to accelerate towards the Earth. It's moving this way, but it's about to accelerate down. So we're using the classic linear motion for right now. Linearly speaking, it wants to move, well, sorry, I was saying to the right because of my own hands. The way I drew it, it's to the left, I apologize. Moon wants to move to the left, Earth's gravity is pulling it down, so it's going to accelerate in this direction, but it's still going to try to move to the left simultaneously, right? We know from our old formulas that your initial velocity still counts until acceleration takes it away. So the moon is going to move to the left while it accelerates down. So the moon doesn't end up here, and it doesn't end up here. It ends up here. It moved forward and down at the same time. See how that happened? Forward and down all at once. Kind of like the way that I would draw projectile motion. An object that is moving in 2 dimensions at once. It is falling, but it's moving forward all at the same time. The moon is technically a projectile. Go figure. Fun fact for the day. So now the moon's here. And interesting thing, all of these vectors have now changed direction because Earth's gravity doesn't automatically point down the way that I've drawn this picture. It points towards the center of the Earth, right? And from the moon's new angle, that direction has changed. So Earth's gravity doesn't pull this way, it's now pulling this way. And this velocity vector has also now changed direction because the moon has accelerated. We know this because the force of Earth's gravity on the moon has caused it to change direction. It's accelerated like how all projectiles accelerate through the air. And the definition of acceleration includes not only a change in speed, it also includes a change in direction. Because if direction changes, velocity changes. And if velocity changes, that's acceleration. So the moon constantly changing direction counts as an acceleration. This force causes acceleration of the moon, and that changes the direction of its velocity vector. It began falling while moving forward, so it moved over here instead, and its velocity has tilted because of that. So now the velocity vector points in a straight line in this direction. So both vectors have changed direction. They're still at a right angle from each other. It's just that the axis has kind of shifted slightly. Still at a right angle, but the whole process has tilted with the motion. Gravity's still pulling the moon towards the center of the Earth, and the moon still wants to rocket away from the Earth in a straight line. And at this point, the process just kind of repeats itself. The moon wants to move this way, gravity's pulling it this way, the moon accelerates, therefore its velocity is going to change direction, and so rather than ending up here or here, it ends up here. It does both at the same time. This process just continues all the way around until it's back where it started. And then it continues happening for as long as the moon is our buddy. This is why the moon orbits the planet. Gravity, again, kind of acts like an invisible leash, like how in the other picture on the previous slide, that rope was acting as a literal leash on the can as it's swinging overhead. So this type of circular motion happens specifically because of this inward pointing force. Notice that this gravitational force is always pointing towards the center of the Earth, because gravity always is pulling towards the center of mass of an object. So this gravity will always pull here. Wherever the moon is, gravity is a straight line from the moon to the center of the Earth. And the velocity vector of the moon is always pointing at a right angle to that force. This unique combination of variables creates this centripetal motion. The force of gravity in this scenario is acting as a centripetal force, causing centripetal acceleration. I said a second ago that because the moon's velocity is constantly changing direction, it is accelerating. It is accelerating because a centripetal force is acting on it and creating what we call a centripetal acceleration. This force is taking the moon's linear motion and forcing it into rotational motion. How's it sound so far? So, main cliff notes so far. Forces can take linear motion and turn it into rotational motion. Objects that want to move in straight line can be forced to move in a circle as long as that force continues acting. The force in question serves as a centripetal force and causes centripetal acceleration. And both the force and the acceleration always have to be pointing towards the center of the orbit. If Earth's gravity suddenly stopped, the moon would slingshot away in a straight line. Like again, if you had a rock in a slingshot, you let go of the slingshot, the rock takes away in a straight line, takes off in a straight line. So if gravity turned off, moon would leave us in a straight line. Likewise, if the sun's gravity turned off, the Earth would move away in a straight line, drifting further away from the sun, and then bad things happen. Everything I just described here with the Earth and moon is true of the Earth orbiting the sun as well. And also the sun orbiting galactic center. And everything else that orbits the sun. And everything that orbits anything, really. Now, likewise, you also have to have this forward-pointing velocity simultaneously, because if the moon wasn't moving forwards, it would just fall. You know, like any object falls. Yes?
If something has like rotational motion, does that automatically mean it has a centripetal force? Like, kind of like with the wheel, how you're saying it comes from the center versus like the cars. Do they both have centripetal?
Good question, and the answer is sometimes. This happens when one object orbits a point outside of itself. This is moon orbiting Earth, can orbiting hand, cars orbiting the center of that weird circular driveway. The wheel is a little bit weirder, because if we consider the tire itself, it's orbiting, well, it's not really orbiting, it's just rotating about its own axis. So the wheel is not undergoing a centripetal force here. It's not undergoing a centripetal acceleration. But if something was stuck to the edge of the tire, that object would, because it would suddenly be orbiting the center of the wheel, and that is a point outside of itself. So these metal pieces, if you consider them separate objects, would be having a centripetal force acting on them and would be accelerating centripetally, but only if you consider them separate parts from the tire. Rocks stuck to your bike or car wheels are technically always undergoing centripetal force, and that's why sometimes when they break away, they just shoot off in a straight line. So it does kind of depend, and I'll try to make it as clear as possible in any given example. We're starting here because lab this week involves this stuff. Does that answer your question?
Yeah, thank you.
You're welcome. So, yeah, just to try to summarize that again. If something is just spinning about its own central axis, that's not centripetal force. If something is rotating a point outside of itself because a force is literally forcing it to, that's centripetal force, centripetal acceleration. Anyhow, I'll try to make it very clear in any given case. Now, before we do the math for centripetal force, I want to quickly define what centripetal force isn't. And centripetal force is not centrifugal force. When I started saying the word centripetal, how many of you thought of the word centrifugal? That's fair enough. They are similar words, and they are used similarly in English vernacular. This is kind of one of the points where common use versus physics use differ slightly. We are going to be using centripetal force in this class. That's why I defined it up top. Centripetal force is a real thing that we are going to calculate and measure. Centrifugal force technically doesn't exist, but it's a word that is still used, so I want to explain what it refers to. Now, back up slightly. When you're riding in a car, either you're driving or riding, as long as you're in the vehicle, say the driver notices last second, oh, I have to turn here, and just cranks the wheel, and the car very suddenly starts turning to the left. So, car was moving in a straight line, and then all of a sudden, veers to the left. While you are inside of this car, you are undergoing a centripetal acceleration, because as it turns out, every single car turn is just part of a giant orbital circle, even if you only go about 90 degrees of it. Like if you held the wheel to the left, you could do a donut in the entire circle, but usually we stop after about 90 degrees. Technically though, when you turn the wheel to the left, you are undergoing a centripetal acceleration, you are orbiting the center of some circle, even if you can't see it. But when this happens, when someone physically really firmly cranks the wheel to the left all of a sudden, and the car starts veering left, what direction do you feel like, you sitting in the car, do you feel like you're getting pulled in? Right. Does that sound consistent with your human sensory experience? Your car veers to the left, suddenly your body lurches to the right and almost feels like you could fly out of the car if there wasn't a seatbelt and doors. All right. That phenomenon, that feeling, is what the term centrifugal force refers to. And I want to stress, this is not the thing that we use in this class, because centrifugal force is a feeling. It's not a real measurable force. When the car turns to the left and you feel like you're going to launch out of the car, there's not actually a force trying to pull you out of the car. Like your body might lurch to the right, but there's not actually a force pulling you to the right. What's happening is your own body's inertia and momentum wants to keep moving in a straight line, right? you're only turning left because you're in the car that's turning to the left. If the car wasn't there, you'd keep moving in a straight line. And that straight line feels rightward from your perspective, because your body is being yanked to the left. Your body is being forced to the left by the vehicle. It wants to go straight, and that feels rightward in comparison. Does that track? And there's not actually a force doing that. That's just your body wanting to move in a straight line. But it feels like a force because, one, you are being forced to the left. There is a force acting on you. It's just technically pulling leftwards. And two, it feels like a force because the human body is kind of made out of lots of separate parts that are all stapled together inside of a skin sac. Sorry for the imagery there. When this happens, it's not just your bones that want to move in a straight line, so does your blood. And your blood now ends up pushing rightward against the outer layer of your body. So your blood is internally pushing to the right, and you feel that. And you can feel that if you just swing your arm around. If you do it enough, you kind of feel your blood rushing to your fingertips, right? The centrifugal force is entirely a human perception thing. There's not literally a force pulling you to your right. Your own inertia, your own momentum just wants you to keep moving in a straight line, and it feels like you're getting pulled to the right because in comparison, you're being yanked to the left. It feels like you want to move to the right in comparison, and your blood is pushing internally in that direction because it wants to go to the right, and it's pushing against your skin to do so. In turn, your skin is pushing leftward on your blood to keep it in your body. All of this has been to once again summarize, we don't use this word, we use this word. Centripetal means center seeking. Century is center, petal is seeking. And it's because the force here pulls to the center always, and therefore you are accelerating to the center always. Centrifugal means center fleeing. Again, referring to the fact that it feels like you're getting pulled out of the circle, even though technically there's no force pulling you out of the circle. So centrifugal force doesn't exist because there's not actually a force pulling you out of the circle. Your body just wants to leave the circle, and the inward pointing force is forcing you to move in a circle. So we don't use this word. Fugal, the F means fake. The F means fictional. We use centripetal in this class. Now, if you're a biologist, you might use or even a chemist, you might use a centrifuge, which is derived from the word centrifugal. That machine technically takes advantage of the difference between these two things to separate objects when you spin them in a circle. But that still technically relies on centripetal force. It's just called a centrifuge because language. I am not a linguist, sorry. So, once again, to summarize this entire diatribe, we like this, we use this. I wanted to at least talk about this, because sometimes the word comes up and the sensory perception comes up, but this is not what this class is about. This is what this class is about. Does that feel okay? Okay, that's why there's no formula for centrifugal force. It's not a real force, it's technically not a real thing. You do feel it. I'm not invalidating your sensory perception. I'm just saying that that's not technically an outside force. That's a quirk of you having blood and limbs. Now then, math. Because we do a lot of math in this class. Centripetal force and centripetal acceleration have their own formulas. Those formulas are, for an object to move in a circle like this, there needs to be enough acceleration to cause its velocity to change enough in order to stay at a specific radius from the center of the circle. The formula for centripetal acceleration, so this is English A subscript C, A subscript C, centripetal acceleration, or I guess acceleration centripetal, is equal to linear velocity squared over the radius of the circle the object is being forced into. In the case of the Earth and the Moon, the v would be the moon's linear velocity, that's the speed it wants to move in a straight line at, squared, divided by the radius between the center of the moon and the center of the Earth. The center is just because this is happening because of gravity, therefore we need to consider the center of mass. So the radius here is distance between the moon's core to the Earth's core, and that is the radius of its orbit. So the centripetal acceleration tells you how much it needs to be accelerating in order to orbit at that distance at that speed. Alternatively, there's a second formula, since this is a rotational motion. Instead of considering its linear velocity, you could also consider its angular velocity, how fast it is rotating the planet, rotations per day or things like that. And there's a slightly modified formula if you want to use that information instead of linear velocity. That would be omega squared times r. So depending on whether or not you know linear speed or angular speed, there's a different version of the formula for that specific use. They mean the same thing. One is derived from the other, just slightly tweaked depending on which one you happen to know. Moon's linear speed is huge. It's actually trying to rocket away from the Earth at several times the speed of sound. Its rotational speed is actually very slow, because it takes it a whole day just to do one lap. So, that is the formula for centripetal acceleration. That centripetal acceleration is caused, dang it, there's supposed to be a subscript there, by a centripetal force. There's supposed to be a letter C here. There we go. Centripetal force causes centripetal acceleration. Some real force has to serve the role of centripetal force. So unlike most of the other forces we've talked about, where there's a very specific case where one of them is acting, like gravity or normal force that have their own rules and always occur in the same places, centripetal force is kind of like a role for an actor in a movie, and some other force has to play that part. Here it's gravity. When you're swinging something by a rope, it's the tension in the string. And there's loads of other scenarios besides that. Although I will say, tension and gravity tend to be the most common ones. Gravity because orbits in space. Ropes because, if something is tied to a rope, it's going to move in a circle if you spin it that way. So tension and gravity are pretty commonly serving as centripetal force, but something has to fill that role. Technically any force can, but some force has to serve the role of centripetal force. And if something is orbiting like this, that force is going to be whatever is constantly trying to pull it towards the center of the circle. So, centripetal force causes centripetal acceleration. When a mass is centripetally accelerating because of a centripetal force, its linear velocity is going to change at a certain rate to keep it at a certain radius from the center of the orbit. The faster something is moving, the more centripetal acceleration it needs to undergo, the more centripetal force is required to hold it in place. Questions so far? All right. Let us utilize this formula before we break for the day. Let's say that I have a 1 kilogram mass. I have tied it to a rope that is 1 meter long, and I am going to recklessly swing it over my head. The object orbits my hand, which is holding the other end of the rope, at a linear velocity of 3 meters per second. That represents the speed the rock would be moving at in a straight line if there wasn't a rope forcing it to move in a circle. So, 1 kilogram mass, orbiting at a distance of 1 meter from my hand. What force is going to cause the rock to orbit my hand? Tension. The rope that's physically tied to it is what's connecting the rock to my hand. Therefore, the inward pointing force from the rope is going to try to pull the rock towards my hand. If that tension didn't exist, the rock wouldn't orbit my hand and it would just move away in a straight line. So, rock is at a distance from my hand, there's a force of tension pulling it towards my hand, and that force is going to act as the centripetal force, causing the rock to centripetally accelerate and move in a circle around me. One sec. So, first question, given what we know, those variables being mass of 1 kilogram, linear velocity of 3 meters per second, orbital radius of 1 meter. What must the centripetal acceleration of the rock be for it to be orbiting at this radius? New formula for centripetal acceleration is v squared over r, or omega squared times r. We know its linear speed, and we know the orbital radius. There's a 1 meter rope connecting it to my hand, so it has to orbit at 1 meter. So AC is going to equal 3 squared over 1. Everything is already in the right units, kilograms and meters per second. So the centripetal acceleration of the stone is going to have to be 9 meters per second squared. That represents how much its velocity has to change every second for it to move in that pattern. Now, from this information, I would like to know what the tension in the rope would need to be to make this happen. And we've already described that tension is going to be serving the function of centripetal force. So when I ask for tension, I'm really asking for centripetal force. Which means we can use the centripetal force formula, centripetal force equals mass times centripetal acceleration, to tell us how much centripetal force is required to make the rock do this, and in turn, that would tell us what the tension in the rope would need to be in order to do this. Now, I conveniently made the rock 1 kilogram, so 1 times 9 would just be 9 newtons of force. The rope has to be able to exert and withstand 9 newtons of force for me to be able to do this. If the rope snaps before that, this doesn't work and the rock just leaves in a straight line. How do you guys feel so far? questions, issues, comments at all with any of the math for these numbers? Okay. Before we break for the day, I just have a few small conceptual questions. This is the required amount of force for the rock of this mass at this distance to orbit my hand at this speed. What happens if I make it go faster?
Increase force and
Yes. If I speed the rock up, so say I'm going at one speed and then I just physically force it to go faster, the velocity will increase, and therefore the required amount of centripetal acceleration will increase. The centripetal force, and therefore the tension, would have to increase along with it. So the faster something moves at a given radius, the more centripetal force is required. Likewise, if the radius changes, that is going to also affect the rest of it as well. Because if the speed stayed the same, but the radius was, say, cut in half, like if I physically pulled the rope shorter instead, if the radius was half as big, that would also increase this number. And that would also increase the required amount of force. So all of these things are directly connected to each other. It's a very fine balancing act, getting something to orbit another object. And that's what lab this week will be exploring. Proving this formula works, looking at various examples of it working. Questions? All right. Make sure you bring these notes when lab happens for you this week. The lecture will continue looking at rotation. Let me know if you need anything or have any questions, and have a great day. Right.
You said any.
Yes, so, oh, sorry. This is FC equals MAC. They just, again, wrong version. Plug this formula in correctly. So, AC is V squared over R. They're squared. No, you're not. First of all, be nice to yourself. You're welcome.